Our initial plan was to have this course jointly delivered by Radu and Arghir Zarnescu. Unfortunately, Valery Slastikov is caught in Kiev. He is dual national Ukrainian and British, but under the martial law there, he cannot leave the country. We're hoping he'll be able to come. So I'm really substituting for him. Okay, so this will be about analysis of point defects in Nematic crystals. And the plan is that I'll do the first and the last lecture, and Radu will do the second and the third lecture. So today I'll start by presenting an introduction to QSR modeling and introducing this Landau-de Gennes theory. And then Radu will continue with a simpler version, let's say, Ginzburg theory, and then he'll talk about mathematical defects, and then he'll do the same thing tomorrow, 2030, but using this more complex Landau-de Gennes theory. And I'll finish by presenting a whole group of what can be done about point defects and a few things about point defects as well. Okay, so this will be a multi-scale presentation in the sense that I'll do the airplane scale with more with slides and modeling physics, and Radu will do the honest mathematics, the board. Okay, so this is it. That's the real thing. That's an experiment. This is something which in real life is about 1 centimeter, so it's under a microscope. And in fact, this is obtained by passing polarized light through a thin layer of liquid crystal. And you have polarizers, which are like foil. So light passes through it, and after it comes out, it can vibrate only one plane. And then you have a cross polarizer that does the same thing, but with light in a different, vibrating in a different plane, right? So if you put two such things, in principle, you shouldn't see anything at the end, right? Because light will come polarized in one plane here, and then this other one will not see any light. So in principle, you will see only dark things, as in here, right? The fact that you see other colors means that when light passes through a thin layer of liquid crystals between cross polarizer, it changes its polarization, right? So that's the main feature of liquid crystals, this optical signature, yeah? And that's how they were discovered actually not so long ago, at the end of the 19th century, right? And then the main thing that you see in this kind of liquid crystals are these kind of long threads, yeah. And that's what gives the name of this kind of liquid crystal. There are many types of liquid crystals. We'll just talk about one's called nematic, and nematic is related to a Greek word nema, which which means threads, yeah. So lines like this. So that's the main characteristic of this material, namely these threads. Yeah, and then there are the thing that we'll be focusing on, namely these defects. Yeah, these are the points, the places where light changes suddenly. Yeah, it's so you see there is sudden transition, right, between nearby regions. Okay, so this is a different scale. It's of the order, or let's say 100, 200 nanometers. Yeah. So nanometer is 10 to minus 9 meters. So very, very small. And the point of looking at something like this is that you'd like to understand what happens in those regions where you have defects, those sharp transitions in color. Yeah. And you cannot really do it with current experimental techniques without really disturbing seriously what's happening in there. So what people do is they simulate. Yeah. So this is actually a simulation of the group of Claudio Zamononi's molecular simulation, and this is partly based on what they expect to happen. And what you have these rod-like molecules. So you know something. These are like small columns, yeah, small cylinders whose the thickness of a cylinder is much more than the length. Yeah. And then you have these nails, yeah, and the main feature of the material is this so-called local orientation. Yeah, so if you look on a small region, you see that all of them will like to stay in one direction. You can go to a nearby region, and you see that most of them will prefer to go in a direction like this. Yeah. So this local orientation of these elongated molecules is the main characteristic of liquid crystals. Now that's what happens, and then the issue is how to model this. In modeling, you also have to take into account the fact that this is not just a material by phase. And what happens is that if you are at a high enough temperature, these rod-like molecules will have no preferred orientation, so this behaves like a liquid. You know? And now, what happens in a liquid once you lower the temperature? If you think of water, you reach some crystalline phase where everything is kind of blocked in molecules on certain lattices. Yeah. What is specific to this material is that there is an intermediary temperature between the high temperature corresponding to isotropic phase and the low temperature corresponding to liquid phase. There is this nematic liquid crystal phase, which is characterized by this phenomena that on small regions you have a preferred orientation. And now you'd like to model this. There are various ways of doing it, and sometimes the most comprehensive way would be to assign a point in the macroscopic space a measure. Okay? A measure of the unit sphere, and that is assigning to any region of the unit sphere a number between 0 and 1. And that tells, that number would be the probability that the molecules are pointing in a direction contained in the surface, in that surface A. You know? Now, if you look at these, they have no head or tail, so you'll have as many molecules pointing, say, in this region A as pointing in this region minus A. Yeah. So this gives you the physical requirement that mu of A is equal to mu of minus A for any region of the sphere. Okay. Yeah. Now, De Gennes had this intuition of simplifying a bit the situation, because having a probability measure at each point in space is, well, complicated. I mean, there are theories that use this, but then things become very hard to simulate. Yeah. So De Gennes had this intuition of not using the whole thing, the whole measure, but just part of the measure. And to some extent, he inspired himself from Landau, who did related things earlier on. So that's why we have this Landau-de Gennes theory. And his intuition was not to use the full measure, but just a moment of the measure. Yeah. So the first moment would be something like this. You integrate with respect to this measure of the unit sphere P. Yeah. But if you do that, you get 0. Yeah, because of this physical symmetry, it's a calculation that because of this fact that mu of A is equal to mu of minus A, that first moment would be 0. So we can look at the next order moment. So what you are integrating here is really a matrix, yeah, because P tensor P is a matrix, yeah. P is a unit vector that has components P1, P2, P3, And then P tensor P is a matrix, a 3 by 3 matrix that has ij component pi, pj. Okay? And then you integrate this with respect to this measure, and you obtain again a measure. A matrix, a 3 by 3 matrix. Yeah. Now, if you had no preferred orientation, this 3 by 3 matrix would be the identity. Yeah. So, if I normalize this second order moment by subtracting this 1/3 of the identity, this gives me a rough measure of how aligned in one direction the rods are. Yeah. Of course, when I do this, I lose a lot of information. Yeah, because I'm replacing a measure with just its second order moment. Yeah, if you think, for instance, if you have a function on the circle and you expand it in Fourier coefficients, and you just pick the second Fourier coefficient and say, okay, this is giving me the whole information. It's a tremendous loss of information. Yet the miracle is that this works for many practical purposes, and this thing that you obtain through this heuristical construction is a 3 by 3 symmetric, yeah. Because if I integrate pi, pj, or pj, pi is the same thing. And then it's going to be traceless, because if I integrate p1, p2, and p3, they add up to 1. So that's a traceless matrix. Yeah. And from now on, I'll just call this a Q-tensor. So the Q-tensor will be just short for 3 by 3 symmetric and traceless matrix. Nothing more. So really, just a matrix that is special.
Here, quick question. Is it useful to distinguish between the projective plane here and this S2 version?
I'll get to it. Now, if you have eigenvectors of Q, yeah, so you have something like this, Q EI is equal to lambda I EI, yeah, and you multiply with EI, then you have this, because these are normalized, you know. So this is 1. This gives you this, well, and you remember what Q is, you get this expression. And then P dot product with EI, which is unit vector, P is unit vector as well. So this is a number between 0 and 1. And this measure is a probability measure, so it's integral is 1. So overall, these lambda are between -1/3 and 2/3. Yeah. So this is to say that in principle, you should be working only with Q-tensors like this, physical Q-tensors that have the eigenvalues between -1/3 and 2/3. Yeah. In practice, I mean, most of the models that we'll be using don't quite always respect this. So yeah, there are various levels where you lose information. Yeah? Even defining this Q-tensor is a loss of information in some sense, but you know, you can have too much information, and you'll see that even a Q-tensor description can generate too much information in some sense. Yeah. Okay, so there is more to these nematic crystals. I should say that it sounds fancy and exotic, but we are watching these things on a daily basis because in our computer displays, in the phones, that's precisely what it is. Even in that projector, you have precisely this material nematic liquid crystal. Yeah? And then you have the same description that is used for other materials as well. Here you see patterns. Yeah, these Y patterns that Valeria actually mentioned yesterday. Yeah, so there is something more universal in this than just about a special exotic material. And in fact, really, this theory for nematic liquid crystals can be used virtually for anything that involves elongated bits. Yeah, in the sense that, for instance, if you have nails, yeah, and you put a stack of nails, they will tend to arrange like that atomistic simulation that I showed before. Yeah, so this is to a large extent a steric effect. If you want to pack things, molecules, or objects that are elongated in one direction, you'll start creating patterns like these special places where you have special behavior, these defects. Yeah, And right, so this technology for describing nematics can be used to a lot of other systems that display the same behavior. And in fact, one of the most successful models for liquid crystals proposed by Ericsson was developed in an abstract way. Ericsson was initially a rational mechanics person, and he sort of designing a model for liquids in which you have elongated molecules. Yeah, so unlike for Newtonian liquids, which are, statistically, let's say, spherical, he was asking himself the abstract question of what would happen if you have elongated molecules. So, he wrote these equations, and then he went and asked people what behaves like this, and they told him liquid crystal. But the reality is that there are many other things that behave like liquid crystal. So this is a more general thing than just about nematic liquid crystal. Okay. Now there are several ways of several theories that attempt to present various levels of description of liquid crystals. So this is one of them, which we call the LDG, Landau-de Gennes, and it attempts to describe this local orientation of the molecules through this Q-tensor. Yeah? And the Q-tensor is a 3x3 matrix, so that's 9 components, and then it's symmetric, so it just has 6 independent components. And given the fact that its trace is 0, it actually has just 5 independent components. So it has 5 degrees of freedom. And there is this classification based on how it's an optical classification. Yeah, it has to do with the way light propagates. So the Q-tensors are called isotropic. All the components of the matrix are 0. Uniaxial if it has 2 equal eigenvalues, and biaxial otherwise if it has 3 different eigenvalues. Yeah, and then there is this. So this was proposed in the 70s. Yeah, very popular among physicists, but cumbersome to use. You'll see that it produces messy-looking equations, even in the simplest case. And then Ericsson proposed a simplification. Yeah, he said, well, basically most Q-tensors are uniaxial, so you can play a bit with linear algebra and say that if you have 2 equal eigenvalues, then you can write a matrix in this special form, namely as a scalar S times a matrix which has this very special form, n tensor n minus 1/3 of the identity, where n is a unit vector. Yeah. So in doing this, you attempt to describe the same local orientation using a simpler object, a 3-dimensional object, because if n is a unit vector, you have 2 degrees of freedom, and then with this scalar, you have 3 degrees of freedom. Yeah. And then there is the older theory of Ozine Frank that takes this to be just a constant, so you can ignore it, and then you describe this local orientation of the molecule just with vector fields. Yeah. So with n in the S2, so that's just 2 degrees of freedom. Yeah. So now you have a way of describing this local alignment of the molecules using either an object with 2 degrees of freedom, 3 degrees of freedom, or 5 degrees of freedom. Yeah. And in fact, it gets more complicated than this, because this should change in space. So you should have matrices that depend on the point in space. Yeah? At each point in space, you have a different matrix. And this is something that you are familiar with. At each point in space, you have unit vector. Yeah? So these are vector fields. But what are these? What are matrix-valued fields? So if you want to have some sort of way of visualizing this, well, this is a nice way that was imagined of how to draw, how to visualize matrix-valued fields. So you can visualize a Q-tensor either as a parallelepiped whose axes are parallel with the eigenvectors of Q, and the length of this parameter that are proportional to the eigenvalues of Q, or an ellipsoid, again, with the axis parallel with the eigenvectors and the radii proportional with the eigenvalues. So basically you have here the same matrix valued field represented either using parallel or ellipsoid, and of course it's a different perspective. This is made like this, and the other one is more horizontal. Yeah. And yeah, patterns like this will try to describe those point defects. And in fact, this is the so-called index 1/2 defect. Okay. Yeah, there is a bit of cheating here when I say that the length or the radii are proportional to the eigenvalues, because the eigenvalues add up to 1, so you need to add a constant to all of them to make them positive. Okay. Okay, so that's the Q-tensor perspective, and then you have this story in the Landau-de Gennes world, and you have this corresponding story, say, in what would be more like Ericsson world. Yeah. So these are attempting to describe the same physical situation, but in here you are using fewer degrees of freedom. Yeah. You have a more crude description, if you want, and the way of transitioning from this perspective to this perspective is, for all practical purposes, to flatten a parallelepiped like this to just its longest axis. Yeah. So if you have such a flattening, you get this this kind of description here. Yeah. And from a mathematical point of view, this will be like a relaxed description of this limit theory. Yeah. The limit theory has the advantage that it's simpler, but you are losing some information, and then you are creating high gradients as in here, which won't be so bad in this kind of description. Yeah. So you have advantages and disadvantages in using a more complex, as in here, description, or a simpler, more geometrical description as in here. Okay. So this is what we are trying to describe. Yeah, using these tools, these matrix valued fields, or these line fields, or these vector fields. And what you are trying to do, the simplest thing in which you can try to obtain some information out of these modeling tools that we developed so far, is the case when you do energy minimization, right? So you have an energy function that involves these Q-tensor fields. So Q is now a function at each point in space. You take the values into this space at each point, which should have been in the function. At each point in X, you take a Q-tensor in the target. Yeah. And then you have this part which says that I look at the derivative with respect to the xk direction. K goes from k goes from 1 to 3. And then I look at the gradient. Yeah, so this is just the gradient of Q squared, and I take the gradient for each component. Yeah, so this is the gradient of Qij squared, and then I sum over all components I and j. Yeah. So this is just saying how I penalize spatial variation. That's quite common in many theories, of course. And then what is specific to this theory is this polynomial here. Yeah. This is the polynomial that attempts to describe this phase transition that I was telling you about before, because it has several coefficients. But the first one is usually assumed to be dependent on the temperature. Yeah. So what happens is that when you change the temperature, when you change A, you'll see that for in a certain regime where A is negative, actually, the minimizer of this is just zero matrices. Yeah. If you lower the A, the minimizer of this starts getting more interesting. Yeah. And the easiest case to see how interesting it gets is when you set, say, b is equal to 0. Yeah, because then if you have something positive here, you'll see that the minimizer of this. So what you have here, you have trace of q squared, and then you have trace of q squared squared. Yeah, so the minimizer will be something like this. Trace of q squared is equal to a constant. Yeah, this is a way of writing trace of q squared. So qij, trace of q squared. And this is actually a 4D manifold. Yeah, because I have in this Q, I just have 5 independent components. Yeah, Q3, Q4, and Q4. Yeah, and then I repeat here, and then Q4. Yeah. So when I write trace of Q squared, this comes as twice Q1 squared plus Q2 squared plus Q3 squared plus Q4 squared plus Q5 squared is equal to a constant. Yeah, positive one, fortunately. So this is really a 4-dimensional here. Yeah. It gets a bit more interesting when b is not 0. So I was told yesterday that I was supposed to do some calculations at the board. So let me try to do that and convince you that for b non-0, the minimizer is actually a 2-dimensional manifold, mainly made of matrices that can be written in this special format. Plus is a number that can be explicitly computed depending on a, b, and c, and is a unit vector here. Yeah, so you get this uniaxial manifold. Yeah, and you see, this looks like a convoluted way of writing S2 in terms of matrices. Yeah, because in here, I mean, this is some constant, and then you have n tensor n. Yeah, so this looks, almost bijective to S2, and well, it's not, because if you put n or minus n, you get here the same matrix. Yeah. So what you have here is really this object that you might remember from geometry called the real projective plane, where you identify antipodal points in on S2, and or you can think of the lines passing through the origin. Yeah.
This is where this differs from the Oseen Frank now. The Oseen Frank.
Yes,
yeah.
Because in here, this is really the real projective plane. So this is a set of lines passing through the origin. Yeah. Okay, so let me do this calculation that says that for B non-zero, the minimizers are uniaxial. And once they are uniaxial, then I can do simpler calculations. So lemma for B non-zero, minimizers of FB are uniaxial. So I remind you that this means IE, they have 3 eigenvalues. 2 equal eigenvalues. Okay. Well, the thing to
press the button.
Okay, here. So FB is something like this. FB of Q is something like A over 2 minus A over 2 trace of Q squared minus B over C over 3 trace of Q to the third plus C over 4 trace of Q squared And it turns out that all these quantities are spectral quantities in the sense that they depend just on the spectrum of the matrix Q. So if Q is a matrix that in the diagonal form looks like this, so it has eigenvalues lambda 1, lambda 2, and say lambda 3 equal to 0, sorry, lambda 1, lambda 2, lambda 3, then you'll have trace of Q squared is, well, sum from I is equal to 1 up to 3 just square d, yeah? Lambda 1 squared, lambda I squared. And then trace of Q to the third is lambda 1 to the third plus lambda 2 to the third plus lambda 3 to the third, yeah? And then I can write this function, defined matrices, as a function of 3 variables, lambda 1, lambda 2, lambda 3, and I minimize that one. So let me call this, say, fd hat of lambda 1, lambda 2, lambda 3. Yeah. So it will be something like this. And this is all squared. And then I want to minimize under the constraint that this is traceless. Yeah, so the sum of these is 0. So let me put here minus this Lagrange multiplier. And if I look at the critical points, I have df d lambda I is equal to 0. This gives me something like this: a lambda I plus, sorry, this is minus b lambda I squared plus c, sum from I equal to 1 up to 3, lambda I squared, lambda I is equal to 0. Okay, so this is from I equal to 1 up to 3. Okay, now I want to conclude that in fact this forces me to have two of these, lambda 1, lambda 2, and lambda 3. Two of these are equal. Yeah. So, well, let's assume that this is not the case. Assume lambda 1 is not equal to lambda 2 is not equal to lambda 3 is not equal to lambda 1. So all of these are distinct. And then what I'm going to do is to subtract one from the other. Yeah. So I'll get something like this: lambda minus lambda j, and then I have here a minus b lambda I plus lambda j plus c, sum from I equal to 1 up to 3 lambda I squared. Yeah, this is equal to 0. Yeah, so this is yeah, for any I and j with any I not equal to j. And since I'm assuming that they are all disjoint, I can divide by this, and I get something like this: a minus b lambda I plus lambda j plus c, sum from 1 up to 3 of lambda I squared. This is 0. Yeah, so this is for all I different from j. So if I do it in particular, say for 1 and 2, now, and then for 1 and 3, say, lambda 1 plus lambda 3. I want to raise it. Sorry, raise this. Yeah. And out of this, I see that I have common this. So I get that B lambda 1 plus lambda 3 is equal to B lambda 1 plus lambda 2. So in particular, lambda 2 is equal to lambda 3. Yeah. Which contradicts my initial assumption that they are always joint. Yeah. So this is just a calculation showing that two of the equal eigenvalues have to be two of the eigenvalues have to be equal, and then you can get to that uniaxial form, because you have uniaxial. Right? Because you have, in general, you can write that the matrix something like this. Yeah, this is just the spectral decomposition of a matrix, symmetric one. So this is real here. So you have three eigenvectors, E1, E2, and E3, and then the corresponding eigenvalue. So you can write it like this. And you also know that the identity is equal to the sum of these matrices. Yeah, that's what it means. Yeah. So if you have two equal eigenvalues, you play a bit with these two pieces of information, and you see that you can write. So okay, let's if you now say that lambda 1 is equal to lambda 2 is equal to lambda, then you also have that lambda 3 is equal to minus lambda 1 minus lambda 2 with minus 2 lambda, yeah, and you plug it in there, and you see that Q is lambda E1 tensor E1 plus lambda E2 tensor E2 minus 2 lambda E3 tensor E3. Yeah, but you know that the sum of these is the identity. So what you have here is lambda identity. So I add and subtract the lambda E3 tensor E3. So it's lambda identity minus 3 lambda E3 tensor E3. Yeah, so this is this kind of uniaxial representation that I was mentioning before. Okay, so just to do a small calculation. Okay.
You say that B equals 0 or not equals 0 is important.
Sorry. So if B is equal to 0, you get a different minimizer. This thing which is like a four-dimensional sphere. Yeah. Okay.
Is there some restrictions on the choices of polynomials and matrices that restrict us? Is there some reason why we're restricted to only the 4D and 2D manifold, or the intermediates?
It's a good question. Not very clear, yeah. And yeah, what makes a difference between B0 and B non-zero? Yeah. Physically, B is small. Sorry, it's non-zero. Yeah. But it makes sense to look at B equal to 0 case as well, because of the following reason, right? You have this is the simplest. I mean, this is the Lagrange system corresponding to minimizers of that energy functional, right? So it's a system of well, in principle, you have 9 equations, yeah, but as I said, out of these Ij, are 9 of them, only 5 are independent. So you have 9 coupled equations, and here you have this Lagrange multiplier that enforces that the Q is trace equal to 0. And in principle, this depends on this elastic constant and then these parameters A, B, and C. But mathematically, you can see that there are just 2 independent constants, and then you can do this kind of scaling, yeah, multiplied by a constant lambda, and divide x by mu, yeah, and then you just see what happens with this change of variables. You plug it in here, and you get something like this. And then you have these 2 degrees of freedom, lambda and mu, that come from this change of variables, right? So at the end of the day, you just have 2 independent variables, say lambda, and you can choose another independent variable, b or a. Yeah. And then I mean, this works only if you are in the whole space, yeah, because then you don't have any obstruction to using periodic notation. And then you have this physical regime when a approaches 0, which is the 2D vacuum manifold. I call vacuum manifold that set of minimizers, yeah, when that potential was attaining its medium. Yeah, and then you have this regime when a tends to 0, which is the more physically relevant regime. But you also have this other regime when a tends to infinity, which through this scaling corresponds to b tends to 0. Yeah, a tends to infinity is not a very physical regime. It would say that you are looking at very deep in the nematic at temperatures which are arbitrarily low. Well, that cannot really happen because it has this physical limitation that it cannot have lower than 0 to be Kelvin. But for all, I mean, it's a limit that is often used in the physics literature because it simplifies the system. Yeah. So the case when b equals to 0 is easier to understand mathematically. Yeah. And gives you some intuition of what happens when b is non-zero. Related to these change of variables, what you should really do is to non-dimensionalize the equation to see what is the correct limit in which you hope to see those defects. Yeah. And this is where the analogy with Ginzburg Landau comes into play. Yeah. So you can. So this is the kind of energy that was before, but L was here. Yeah. So if so, I'm trying to minimize an energy function. So if I multiply by L, if I multiply it by a constant, that won't change the minimizer. Okay. So I can put the L to divide by L here. And also, what I'll do is to subtract the minimum of this polynomial in Q, because this in general the minimum is negative, yeah. But it's okay if I subtract the minimum here in an energy function. If I remove a constant or I add a constant, that won't change the minimizer. Yeah? So I change a bit the energy functional and put it in this form where this is now a non-negative polynomial. And which becomes 0 if and only if Q is in the vacuum manifold, which, as I said, can be generically is a 2D manifold, homeomorphic to this real projective plane, but in some limit cases it can also be a 4-dimensional sphere. Yeah. And then what happens is that in a suitable non-dimensionalization, where you take into account those scales that I was mentioning at the beginning, yeah, you see that L is a small constant. Yeah, so you have this situation which is quite often used. In particular, is this Ginzburg Landau theory that Radu will mention in the next hour, where you have vectors, yeah, instead of matrices for a 2D or a 3D domain, and you have this kind of energy functional, right? So here you are vectors, and you have a similar story. Now you want to understand what happens with the minimizers for this energy functional when you have a small parameter here. Yeah. And intuitively, it's kind of straightforward to see what happens with the minimizers, say in this setting. If epsilon is very small, you would like that the norm of u is close to 1. It's also very close to 1 to compensate this. Yeah. So in the limit, when epsilon tends to 0, you'd like to minimize this, yeah, subject to U being unit length, taking values into the sphere. Okay. And a similar story happens here. You'll be interested in studying what happens when L tends to 0. Yeah. And then you'll want this Q to take values into this. Yeah. So if you take boundary conditions which are already in Q-mean, otherwise you'd create a boundary layer near the boundary. So avoid that. You can consider this limit minimization problem. You minimize just the spatial variations, and nevertheless you restrict yourself to functions which take values into this two-dimensional manifold Q-mean. And it turns out that if you want to use this representation of Q-mean in terms of these unit length vectors, you can write gradient of Q as, I mean, this is a calculation at the end of the day. Gradient of Q is 2 times s plus squared gradient of n squared. So this reduces essentially to this minimization problem. Minimize gradient of n squared, where n takes values into s2. Yeah. And well, this is just the Dirichlet energy, really, but for with a constraint. Quite a heavy constraint that n is a unit length vector. Yeah, Dirichlet is just for scalars. Okay, so this is how you see mathematically this relationship between the matrix valued functions and the Q-tensor theory and this say limit, if you wish, vector valued theory. So for the typical point defect in 2D, which is what we'll really focus on throughout the lecture, let me tell you a bit about these things that we'll mention again and again. The index. Yeah. So the index is a topological invariant that is used to classify functions between manifolds of the same dimension. In our case, we'll be interested in functions from S1 into S1. So has F S1 into the complex plane, F reverse S1 into the complex plane, and then you have this index, or degree, depending on what part of the mathematical theory is come from. Or in this case, this is also called a winding number, and in some sense, this is the most intuitive thing because you can think of these. You can represent these as something like this. Yeah. The way of drawing. And this number, in principle, is something that tells you how many times this field rotates when you go around the circle. Yeah. So it's an integer, yeah, which is something like this. If I'm something like this, sorry, index. This is really what it is. F1, this is Z, yeah. And the prototypical examples are f of z is equal to z to the power n. Yeah. So in particular, if you have f of z is equal to z, which is something like this, f of x over 1n. Yeah. So this radial thing, this is index 1. Yeah. So that rotates just once as you go around the circle. If you have two that it rotates twice. Yeah. And you can do also something from RP1 into RP1. Yeah, so these are like, this is like S with this, this is really S with antipodal points identified, so the line fields instead of vector fields, and you have something as in there, say on the left, so you can see that as you go around the circle, you rotate, you don't have a full rotation, but just part of the rotation. Let me try to clarify what's in there. What's in there is something like this. Yeah. If you go around the circle, say, I put tangent here, yeah, and then here I put just in this direction, yeah. So on this part, I put f of z is equal to say E2, and in this part I put f of z perpendicular on z. Yeah. So tangent. Yeah. So so if I go around, you see, I don't make a full rotation. Yeah. If I try to turn this into a vector field, I'll get a problem because I have something like this. Yeah. So I have here. But then I started with the arrow in the other direction, right? So this is an example of a situation where you see a difference between line fields and vector fields, yeah? And for vector fields, you get, instead of this index being an integer, you have that the index can belongs to, well, which is a way of saying that you also have index of the integer divided by 2. Okay? So, this being said, this is a way of having the same story as before, but now with Q-tensor fields. And the advantage in here is that you won't have a singularity. Yeah, these are nice things, but they have infinite energy. If you use this kind of representation, you won't have a singularity at the origin. So that's nice. You avoid the singularity by using this more complex behavior allowed by the Q-tensors. You know. And well, you get something, you lose something, and what you lose is you create a more flexible theory in which you have multiple solutions. Yeah, you have this x over mod x boundary conditions. Yeah. But then you can have various things happening as you go towards the center. Yeah, so it can flatten like this, it can go into the third direction like this, it can go into the third direction and then rotate like this. Yeah. So what so with the Q-tensor theory, you get rid of this problem that you have infinite energy for the core of the defect, but you have this issue that you get multiplicity of the solution. Yeah, and that if you want to do qualitative analysis, that's the main enemy in that, because you don't know which solution you are trying to describe. Yeah, and then that's something that is hopeless for today. So let's leave it.
And tomorrow I will leave it for you.